Hello, 8th graders, Algebra 1 students. This video is not going to begin from the beginning in terms of exponents, because when we were together, we had several lessons on that, several worksheets that you did yourself in class. And earlier this week, I had you watch some videos for review. I had originally made them for 7th graders to introduce them to this topic for the very first time, but it never hurts to reinforce the basic foundations of knowledge. That's always something that could be in play. So hopefully you watched those videos that I asked you to earlier this week. And before we sort of finish exponents, at least for now, want to remind you of the three basic rules from which all of the other rules are derived. X to the m times x to the n being x to the m plus n. When you raise a power to a power, x to the m raised to the nth power is x to the m times n. And then number three, occasionally you'll have need of what if you have more than one base? What if there's an x times a y raised to the m? Well, each of these gets raised to the m power, so that comes in play as well. And the learning of exponents for Algebra 1 is mostly about what can the m's and the n's be. We start with an understanding that theoretically third graders could understand this. We don't generally introduce students to exponents until maybe 5th grade, but there's no reason a third grader can't understand exponents, because x to the third, for example, is just an abbreviation for what it means is x times x times x, multiply three x's together. And we first learn about exponents when they are restricted to what are called the natural numbers. The natural numbers are 1, 2, 3, 4, 5, 6, and so on, not including 0. So what we're going to do is, what we have done and what we're going to kind of finish, at least for a while, is what else can the n be? What else can the exponent be? The m or the n from the previous rules. Well, we got the natural numbers. It's, pardon the pun, it's natural now to ask, what about 0? And you should know by now that any number raised to the 0 power is 1, except for 0 to the 0 power. We say that 0 to the 0 power is undefined because you sort of have two conflicting views at work. Most numbers raised to the 0 power would be 1, but we don't say that 0 to the 0 power is 1, because 0 to any power logically should be 0. 0 to the third power, 0 to the 10th power. You see, multiplying repeated zeros together gives you 0. So you sort of have a conflict when you have 0 to the 0 power. It could go either way, so we say that it's undefined. But as long as x is not 0, x to the 0 power is 1. And we saw why that's true. It's counterintuitive, but it's based on rule number 1, which is why it's rule number 1. If you have x to the 0 times x to the 3, rule number 1 tells us to add the exponents, and we would, of course, have x to the third. But then we look back and we say that, okay, we multiplied x to the third by something and got x to the third, so that something has to be 1. We've seen this before, and hopefully that'll be something that you're good with going forward. And by the way, it's not a proof. What I just went through as far as x to the 0 being 1 is not a proof. It's what's called a definition. We say that x to the 0 equals 1 because it works in conjunction with rule number 1. So now we have, we can understand and deal with exponents that are whole numbers. Whole numbers are the natural numbers, and also 0. 0, 1, 2, 3, 4, 5, and so on. The next place to go would be, what about integers? What about the opposites of the whole numbers? What about x to the negative 1 or x to the negative 2? Well, we've already seen, I have explained why, when you raise x to the negative 1 power, The negative 1 power holds a special place. It's very useful, very valuable in math. When you raise a number to the negative 1 power, you get its reciprocal, the reciprocal of the base. Now, if you look over here, we've got 1 over x, so the x cannot be 0. You cannot have 0 raised to the negative 1 power because that would produce 0 in the denominator, which we cannot have. Why is x to the negative 1 power the reciprocal of x? Why is it 1 over x? Because it works. Again, in conjunction with rule number 1 and what we just saw with the 0 power. Let's imagine x to the negative 1 times x to the 1. And by the way, x to the 1 is x. That's intuitive. That's the way we would expect it to be. X to the 0 being 1 is counterintuitive, but x to the 1, as you would expect, is x. And that works with rule number 1 as well. If you have x times x times x, which is x to the third, and then you imagine x to the 1 times x to the 1 times x to the 1, rule number 1 would tell you to add the exponents. 1 plus 1 plus 1 would give you the 3. So x to the 1 being x works. Now what about this? Rule number 1 tells us to add the exponents. And we would get here x to the 0. Negative 1 plus 1 is 0. So this is x to the 0. But we've already decided, we haven't proved, we've just asserted and defined that x to the 0 power is 1. So now we look back. We just multiplied x by something to get 1. So that something is the reciprocal. We can put 1 over x in place of the x to the negative 1 and get 1, right? 1 over x times x is, whoops, miswrote that. 1 over x times x is x over x, which is 1. So that 1 over x can be placed where the x to the negative 1 is. So that's why we can logically define x to the negative 1 as 1 over x. The next question is, what about the other negative integers? What about x to the negative 3 or x to the negative 10? Well, we're going to use rule number 2 for this. X to the negative 3 power. Okay, how are we going to interpret that? This way. We're going to think of it as x to the third power raised to the negative 1. X to the third power raised to the negative 1. This is the rule number 2 situation. And by the way, let me just give you a quick reminder about rule number 2. Why is it that x to the third times x squared is x to the fifth, whereas x to the third raised to the 2 power is x to the sixth? Down here, I just have a little reminder about rule 1 and rule 2. Right? X to the third times x squared. This is 3x's multiplied together times 2x's multiplied together is 5x's multiplied together. So it's x to the fifth. We add the exponents. But what about this one? This is rule number 2. This is the case where we multiply the exponents. Rule number 2 tells us to do 3 times 2 to get the 6. Is that arbitrary? No. It actually can go back to rule number 1 because x to the third squared, right? What does it mean to square something? Well, it means to multiply it by itself. X to the third squared is x to the third times x to the third. Now we're back to a rule number 1 situation, right? This is where we would add the exponents. This is 3x's multiplied together times another 3 for a total of 6, where we would add the 2 exponents. But rather than look at it that way, we can take a shortcut and just do 3 times 2 to get the 6. So a little review of rule number 1 and rule number 2. And rule number 2 is valuable. It might even be necessary in order to understand x to the negative 3. We'll think of it this way. And rule number 2 would tell us to multiply the exponents. 3 times negative 1 is negative 3. So this is a straightforward application of rule number 2. Okay, well, we've already seen that when you raise a number to the -1 power, it's the reciprocal. So x to the third to the -1 is 1 over x to the third. We've handled now all of the integers. We can handle any negative integer exactly this way. Now, before we move on to fractional exponents, that's the last piece of the puzzle. We have to understand how to raise a number to a fractional power or a negative fractional power. And of course, fractions together with negative fractions are known as the rational numbers. So this entire topic is known as rational exponents, rational number exponents. We have to get to the point, for example, just throw a quick one out there for you. We have to get to the point where we can handle something like this. 8 raised to the -2/3 power. We can do that, but we're going to hold off on that for the moment. And talk about what we often do in math is when we're trying to get to a general rule, we start with easy specific cases. So let's start with raising a number to a fraction, a positive fraction, where the numerator is 1. Right? We'll come back to this one here. And if we're talking about fractions where the where the numerator is 1, the simplest fraction, I guess, we can start with 2, 1/2, 2 in the denominator. So what does it mean, for example, to raise the number 16 to the 1/2 power? Okay, well, I'll tell you that we're going to say that raising a number to the 1/2 power is the same as taking its square root. And remember that when we write the square root sign, it's understood that there's a little 2 in here. The number that's in that little v is called the index of the root. Well, mathematicians like to be lazy and make things as simple as possible, so they agreed a long time ago to just say, okay, if we mean the square root, we won't write the index in there. But if we want to take the cube root, the fourth root, the fifth root, we would put the index in there. So we define a number raised to the 1/2 power as being the square root. So 16 to the 1/2 power, of course, is 4. Okay? Why is that true? Well, let's look at the general case. And again, this comes back to rule number 1. Let's consider x to the 1/2 power. If we multiply that by itself, rule number 1 would tell us to multiply the exponents. Rule number 1 would tell us to add the exponents. Math is about precision. You have to be careful what you speak and what you write. Rule number 1 tells us here to add the exponents. 1/2 plus 1/2 is 1. So this is x to the 1 or x. But now we look back at what we just did. We multiplied a number by itself and got, we multiplied x to the 1/2 times x to the 1/2 and got x. And that should remind you of something. It should remind you of the square root of x. That's exactly what the square root of x is all about. If you multiply the square root of x by the square root of x, by definition, you get x. So these must be the same. And again, it's a definition. It works. We define x to the 1/2 power to be the square root of x because it works with the other things that have already been established about numbers. And this would work in a very similar way with, for example, let's take 1/5. We'll skip from 1/2 to 1/5. And let's consider 32 to the 1/5 power. The way we're going to define that is the 5th root of 32. This is equal to the 5th root of 32. And notice I put the 5 in there for the index. You see why? let's multiply 32 to the 1/5 power, 5 of them together. 32 to the 1/5 times 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 32 to the 1/5. Just barely had enough room to write it there. Rule number 1 would tell us to add these exponents. 1/5 plus 1/5 plus 1/5 plus 1/5 plus 1/5 is 1. So all of that is equivalent to 32 to the 1, or 32. We just multiplied 5 of these same numbers together to get 32. So that 32 to the 1/5 is exactly what the 5th root of 32 is. We substitute here the 5th root of 32. For each of these. And when you multiply 5 fifth roots of 32 together, by definition, that's 32. That's what the 5th root of 32 is. The number that you multiply 5 of to get 32. And by the way, you can abbreviate all of this as the 5th root of 32 to the 5 power. Right? The 5th root of 32 to the 5 power. And that's 32. Right? And going back to our original, 32 to the 1/5 power raised to the 5. Now this is a rule 2 situation, which tells us to do 1/5 times 5, which is 1. So it's 32 to the 1, or 32. And by the way, I intentionally chose 32 to the 1/5 because that's a rational number. Another huge aspect of understanding roots is to realize, is the root I'm dealing with rational or irrational? Well, the 32 to the 1/5 power is rational because what's it equal to? What is the 5th root of 32? It's 2, right? And these rules work whether what you're dealing with is rational or not, whether it's rational or irrational. For example, 10 to the 1/3 power. 10 to the 1/3 power is, by definition, we say that it's the 3rd root of 10. Okay, so the rule still works, even though this number, whether you write it this way or this way, is irrational. And you should realize that it is somewhere between 2 and 3. If you type into a scientific calculator the cube root of 10, or 10 to the 1/3 power, the calculator will display 2 point something, right? Because 2 to the 3rd is 8, and 3 to the 3rd is 27. So anything between 8 and 27, the cube root is going to be between 2 and 3. So hopefully now you're comfortable with raising a number to a fractional power where the numerator is 1. All right, let's continue. What about 8? I'm sorry, let's change that to 25 to the 3/2 power. Notice now that the numerator is no longer 1, the numerator is 3. Rule number 2 is going to allow us to define this. We use rule number 2, recall, for negative exponents. When we were dealing with the negative integers, we used rule number 2. If you look back, raising something to the, when we raised x to the, let's say, -3 power, remember that? We said, let's think of it as x to the 3rd to the -1. There's the rule number 1, multiply the exponents. And of course, this becomes 1 over x to the 3rd. Well, we're going to use rule number 2 here as well. And we're going to think of it this way. We're going to think of 25 raised to the 3/2 power as 25 to the 1/2, and then raised to the 3. Rule number 2 tells us to multiply these two exponents. 1/2 times 3 is 3/2. And again, I chose one that's very simple. Do you see now in standard form, fully simplified, what is 25 to the 3/2? Do you see that it's 125? Because 25 to the 1/2 power, that's the square root of 25, which is 5. So it's 5 to the 3rd power, which is 125. When teaching middle school math and Algebra 1, I will frequently use the word rigged. Very often the problems that we're asked to do by the textbook authors or the teacher are rigged to work in a certain way. This one was rigged because the denominator was 2. That indicates square root. And 25 is a perfect square. The square root of 25 is 5. So this one worked out nicely. Now, another thing about math is very often there's an easy way and a hard way to do something. This was the easy way to do this problem. You might have wondered, well, could we have represented this as 25 to the 3rd power and then raise that to the 1/2? Now, multiplication is commutative. Multiplication is commutative. So this is equivalent to what I did earlier. What I did earlier was 25 to the 1/2 raised to the 3. Okay, 1/2 times 3 is 3/2. 3 times 1/2 is 3/2. You see why this is so much more difficult. To evaluate this, you have to do 25 times 25 times 25, and then take the square root of it. Now, I guarantee you this will come out to be 125, just like the other one did. You can try it if you like. Do 25 to the 3rd power, get that on a calculator, and then hit the square root key. You're going to get 125 just like we did before. But the first way that I did it was much easier than this. So try to keep that in mind. And we really only have one more situation to deal with. What if we're trying to raise a number to a negative fraction exponent? Well, I gave you this one earlier, said we'd get to it. I guess the time is now. We're actually going to use an extension of rule number 2. One of the things it kind of came up earlier, I did, I think it was 32 to the 1/5 times 32 to the 1/5, 5 of them, remember? And I said, we'll add the exponents. Well, the rules are given in simple form. They can be extended. So, for example, x to the m times x to the n. Now, we know that's rule number 1. It's x to the m plus n. But it can be extended to this. Notice I avoided the O. We don't usually use O because it looks like a 0. So this would be x to the m plus n plus p. It's just an extension of rule number 1. And rule number 3 can be extended as well. We're going to have to do that here. We're going to have to extend rule number 2. Here's how we're going to think of 8 to the negative 2/3 power. We're going to think of it as 8 to the 1/3 raised to the 2, and then raised to the negative 1. Notice the nested parentheses here. Sometimes we have a need to write nested parentheses like that. Now, I'm not suggesting that you have to write this all out like that. You should get to the point fairly soon where you can do this mentally. But let's understand how I set it up and why. First of all, an extension of rule number 2, right, would tell us to multiply these 3 exponents together. 1/3 times 2, 2/3 times negative 1, negative 2/3. And let's work from the inside out. 8 to the 1/3 power is 2, right? The cube, that's the cube root of 8. That's why I chose, see, when I chose 8 and a denominator of 3, that was a nice situation that's going to produce a rational number because I knew that the cube root of 8 is 2. So we have 2 to the 2 power raised to the negative 1. The 8 to the 1/3 is the cube root of 8, which is 2. So then we have 2 to the 2 to the negative 1. 2 to the 2 is 4. So it's 4 to the negative 1. And 4 to the negative 1, of course, we've already defined that to be 1/4. So the original 8 to the negative 2/3 works out to be 1/4. And I see that we're about 25 minutes. I'm gonna stop it there. I might think of a few things to bring up later, but I think that's enough for now. I think if you put everything together, what we did in class when we were together, those review videos that I've asked you to watch, some of the work that you've done in IXL, you should be pretty well prepared to deal with any rational number exponent. So take care for now. I'll see you soon.